Hello and welcome back. Today we're going to be going over 3 classic math proofs. So today we're going to prove the formula for the sum of the first n squares, that 2 to the power of 2n minus 1 is always divisible by 3, and the formula for the sums of the first n even numbers. So we're going to start off by proving the formula that 1 squared plus 2 squared all the way up to n squared is equal to n times n plus 1 times 2n plus 1 all divided by 6, where n is greater than or equal to 1. So the way we're going to do this is by mathematical induction. So with mathematical induction, the first thing that we want to do is have a base case. So the base case for us is when n is going to be equal to 1. So what we do is we just try with left side and the right side. So for left side, so left hand side is just going to be 1 squared. So that obviously is just going to be equal to 1. But now we want to try our right hand side as well to make sure that they equal. So we plug in 1 for n, so this becomes 1 times 1 plus 1 times 2 times 1 plus 1 all divided by 6, which becomes 1 times 2 times 3 all divided by 6, which equals to 1, which means that the base case works. So now what we need to do for mathematical induction is create our hypothesis. And we do this by assuming that the formula is true for k is greater than or equal to 1. So this means that we're going to assume that 1 squared plus 2 squared plus all the way up to k squared this time is equal to k times k plus 1 times 2k plus 1 all divided by 6. And this will be our induction hypothesis. So now for step 3, we need to prove the formula for k plus 1, which is our last step of mathematical induction. So we want to look at 1 squared plus 2 squared plus all the way up to k squared. But since it was up to k plus 1 this time, we need to do plus k plus 1 squared. But we already know from our assumption what 1 squared all the way up to k squared is. This is going to be k times k plus 1 times 2k plus 1 all divided by 6, plus now our missing part, which is our k plus 1 squared. So now what we're able to do is if we look at both of these numbers, we're able to factor out a k plus 1. So this becomes k plus 1, and then a large bracket with k times 2k plus 1 divided by 6 plus k plus 1. And now, in order to add these properly, we need to just have them under the same denominator. So this is going to become k plus 1 times, so this is just going to become k times 2k plus 1 divided by 6 plus 6 times k plus 1 divided by 6, which when we add those together, our k plus 1 will stay on the outside, and then it's all going to be over 6. And then the inside of this bracket simplifies to 2k squared plus 7k plus 6. So now this is our whole expression. Now what we're able to do is simplify our 2k squared plus 7k plus 6. So now the ways that you could do this is either with the quadratic formula, or you could just factor it. So for us, we're just going to factor it. So I'll make a note. So we're going to factor, and we're going to get 2k squared plus 7k plus 6 is equal to k plus 2 and 2k plus 3. Which means that our equation simplifies to k plus 1 times k plus 2 times 2k plus 3, all divided by 6. And this is exactly what the formula would be if you had n equal to k plus 1, which means that the formula holds for when n is equal to k plus 1, and by induction it holds for when n is greater than or equal to 1. So that's the first proof done. So now we're going to prove that 2 to the power of 2n minus 1 is divisible by 3. So this one is going to be short and sweet using modular arithmetic. So we're going to start off with an observation that 2 is congruent to -1 mod 3. So now what we need to do is raise both sides to the power of 2 to the n. So we get 2 to the power of 2n stays congruent to -1 to the power of 2n mod 3. And since 2 to the power of n is always going to be even, this means that we can have, I'll write as a note, -1 to the power of 2n is equal to 1. So this means that 2 to the power of 2n is congruent to 1 mod 3. And now if you subtract 1 from both sides, this gives us 2 to the power of 2n minus 1 is congruent to 0 modulo 3. Which means that 2 to the power of 2n is divisible by 3 for every integer that n is greater than or equal to 1. Now finally, we have the proof of the sum of 2 plus 4 plus 6 all the way up to 2n. So we're going to call this, we'll call the sum s. So we'll set s equal to 2 plus 4 plus 6 all the way up to 2n. And now what we can do is, since they all have a 2 or a factor of 2n, we can factor out our 2. So this will become 2 times 1 plus 2 plus 3 plus all the way up to n. But we know the formula for the sum of the first n integers. I'll write a note, because we know that 1 plus 2 plus all the way up to n is equal to n times n plus 1 over 2. So we're able to set this up as equal to 2 times n plus 1 all divided by 2. And the 2's will cancel out, giving us that s is equal to n times n plus 1. Which gives us our final answer, as the sum of the first n even numbers is n times n plus 1. And that's it, the 3 classic proofs. If you found this helpful, make sure to let me know which proofs you want to see next, and I'll see you in the next one.